Hello students, welcome to EPG Pathshala. I am Dr. Archana Singh from the All India Institute of Medical Sciences, New Delhi. And today we're going to talk on the module Gas Chromatography, Principles and Applications from the paper Techniques in Molecular Biophysics 1. After completing this module, you should be able to describe the principle of gas chromatography, list the various components of the gas chromatographic system, describe the overall process of gas chromatography, and list the different types of detectors used. You should also be able to list the different applications of gas chromatography. So now, before we go into the details of the process and applications of gas chromatography, I will tell you a little bit about some technical terminology that is necessary for understanding the process. Of course, you must have heard the terminology before in the context, but it needs to be repeated in the specific context of gas chromatography. So the first important aspect is the resolution, that is a measure of how well two elution peaks, that is how well the peaks that you are observing on the chromatogram can be differentiated in a chromatographic separation. So the relevance of this can be understood by the fact that if you have two compounds that do not separate out, you will simply get a peak that is broader, but you will not be able to distinguish them completely, as a result of which neither their relative percentage in the sample can be made out, nor can their retention times be defined. The second important thing, which has a lot to do with the kind of detector that is being used, is the sensitivity, which is basically the minimum quantity of material that can be distinguished from the background. So we understand that there will always be a minimum amount of background in each of the samples that we are running. That is a background that will always be detected by the detector, and the ability of the detector to distinguish the actual analyte in your material is a measure of its sensitivity. So typically gas chromatographic processes and detectors have a sensitivity of anything from nanogram to picogram to femtograms. Then selectivity is a very important property, which basically is the ratio of the amount of a compound that does not contain the selected property that generates the same signal as a compound with the selected functionality. So what I'm trying to say is the ability of your detector of your gas chromatographic system to be able to distinguish two similar compounds. Then finally, there is the dynamic range, which is the usable or the operating range over which the detector will generate a changing signal as the amount of analyte changes. Now, understandably, your dynamic range has to be linear, so we mostly refer to it as the linear dynamic range. Also, understandably, the dynamic range, the lower limit of the dynamic range, will be affected by the limit of detection for that analyte, whereas the higher limit will be defined by the saturation of the detector. So, as you may already be aware, there are different kinds of chromatography, and based on the type of arrangement of the stationary bed, they may be described as either column chromatography or planar chromatography. Now, based on the principle of the separation, the column chromatography may be liquid chromatography, in which the mobile phase is a liquid, or it may be gas chromatography, which again is subdivided into gas solid and gas liquid chromatography. Similarly, liquid chromatography, as you may have discussed earlier in earlier classes, is also divided into multiple types like ion exchange, etc., based on the principle of separation. Planar chromatography, on the other hand, is divided into thin layer chromatography and paper chromatography. So the basic principle of gas chromatography involves the movement of a gas phase over a solid stationary phase or over a non-volatile liquid phase. Now, gas chromatography is typically applied to compounds that are non or semipolar, or volatile or semi-volatile, or are amenable to conversion into compounds with these characteristics by a process called derivatization. Now, as I said, either it can be the gas phase moving over a solid stationary phase, in which case it is referred to as gas-solid chromatography, or moving over a non-volatile liquid phase, which is by far the more common. And so all that we shall discuss subsequently will be related to this. Now, the separation principle of gas chromatography involves adsorption or absorption. Remember, differential adsorption or absorption over a stationary phase. And the separation will depend on how strongly the sample compounds interact with the stationary phase, which means that, say, in a group of analytes present in the same sample mix, a stronger interaction will mean that the compound resides for a longer time within the stationary phase, and so it will take a longer time to come out of the column. Now, each of the compounds in a mixture will come out at a time that characterizes it given the same set of conditions for a certain program. This characteristic time is called the retention time. That is, this time is characteristic for a specific compound under a given set of conditions and is called the retention time. Now, this retention time characterizes the compound in the mixture under a given set of conditions and can also define it in these set of conditions only. Of course, to finally identify your compound of interest, you have to compare the retention time of the compounds in your unknown sample mix with that to a known mix called a mix of standards. Ultimately, sometimes when you are still not sure about your compound, you can use a known compound to spike your sample and then arrive at a conclusion as to the peak that you are interested in distinguishing is actually the compound of interest. The final detection of your compound that is being eluted or is coming out of the column is based on the kind of detector you're using. Also, these detectors may be mass or concentration based, and we shall shortly see the wide range of detectors that are available to be linked to the column and which are used based on the selectivity that you desire for your mixture and the expected nature of your sample. So now I will show you a process overview of the GC process. Now, as you can see, this is a flow diagram that is showing you the initial process, whether you're directly injecting the sample on the column or your sample is derivatized, and or you're using the split or splitless mode, the details of which I shall shortly discuss. Now, the sample then goes into your injector chamber, the injector that is right in front, the injector that is right, repeat, injector that is written in front of you. And depending upon the injector temperature and septum, these things have to be finalized before your protocol or before your methodology is put into practice. Then the GC method for which your system is programmed will lead to the resolution of your sample into its different component parts. One of the important components of the GC method will be the column type. Then, depending upon the type of a detector which you have chosen based on the expected analytes in your sample, and then, as we said, there are multiple types of detectors which may be the universal type or which may be specifically selective for a certain kind of compound, there will be an output signal. It is basically this output signal which you perceive in the form of a peak. And finally, to your right is the list of different kind of detectors that can be utilized with a GC system. And as you can see, there's a wide variety available, which is one of the features, key features that makes the GC process so diverse and so adaptable to analyzing different kind of molecules. This slide shows you the basic principle of chromatographic separation. And as you can see, the tube in front of you has been divided into two parts. The upper darker half shows the mobile phase, whereas the lower lighter blue is the stationary phase. Now, as expected, your molecule is being carried, or your sample rather is being carried in the mobile phase, which is the gas, which is part of the terminology, which is gas liquid chromatography as stated earlier. So as the molecules are being carried in the mobile phase, each of these analytes or molecules within the sample will interact differentially with your liquid stationary phase. So understandably, the molecules that will interact more with your stationary phase will move slower, and the molecules that are attracted to the mobile phase or that interact less with the stationary phase will move faster. Thereby, the samples that are moving faster will elute out earlier, giving you the peaks that you observe on the chromatogram at a more early time or at earlier time, which is a characteristic of that molecule under that set of conditions. Now, the key components of a gas chromatographic system are the carrier gas, which should be inert. It should allow a sufficient detector response, however, and combustion when needed. The other key component, in fact, the heart of the gas chromatographic separation process, is the column, which is the key factor that affects the resolution, that is, the ability of the system to resolve two compounds completely. The column may be of a packed type or a capillary type, and although packed columns were much more common earlier, now it is capillary columns that are the most frequently used. Then the final crucial element in the gas chromatographic system is the detector, and these are again of multiple types and of varying sensitivities, and in fact it is the wide range of detectors that are available to be attached to the gas chromatographic column system that has made this technique so versatile for analysis of all kinds. Now, slide 10 is showing you the typical layout of a gas chromatograph. Of course, this is a schematic diagram, and I shall show you the components of a GC system as well later. But as you can see, there is a carrier gas supply which carries your sample through. You put the sample in the injection port, and then the sample is carried along with the carrier gas through the column, and the column that I have represented here is the capillary column. Then as it elutes out, the detector will detect it based on whatever principle your particular detector for your analyte mix is, and the data system or recorder will give you an output. This particular slide also shows you the gross appearance of a column. Now, as we shall see shortly, the temperature in the injection port is very important because, as we have discussed earlier, the sample that needs to be analyzed has to be volatile or semi-volatile, and to volatilize this, what is typically done is that the temperature of the sample port, that is where it is injected, is usually about 50 degrees centigrade higher than the boiling point of the least volatile component in the mix. So here is the injector chamber, or the typical construction of an injector chamber that you typically see in a GC system, and it is constructed this way because our injection of the sample may be split or splitless, which means that either the whole of your sample goes into the column or is loaded onto the column, or only part of it is loaded onto the column. The rest of it in the split mode is basically removed through the split outlets. This is done when you expect your analyte concentration to be very high and you do not really want to put in so much sample into the column. So as you can see, the injector chamber has a rubber septum, and the syringe that loads the sample onto the column ruptures the septum. Then the sample is vaporized There's the carrier gas inlet to one side, which will carry the sample onto the column, and then there's the split outlet, which will remove the sample that does not need to be loaded onto the column. And finally, you see the column just below the vaporization chamber, where the sample is volatilized and then put on to the column. And the injector chamber, the lines in blue, is with a glass liner, which prevents its inert glass liner, which prevents the reaction of any of the analytes in your sample with any other material. Now we keep repeating the term columns again and again, and we realize that it's actually the column that is the heart of the gas chromatographic system. Columns come typically in two types. They can be either packed columns or they can be capillary columns. Most of the columns that are in use today are no longer packed columns. However, for preparative work, packed columns are still used, and one of the benefits of a packed column is its higher sample capacity. That means that the column can take much more sample in terms of amount than can a capillary column. In a packed column, typically the column tubing is packed with small spherical inert support onto which your stationary phase will be present or bonded. Then, as I said before, the inner diameters can range from 1.5 millimeters to 6 millimeters, and it is because of this that one of the reasons is that the packed columns have much higher sample capacity. However, compared to a capillary column, they will be less efficient and the resolution will be much less. As against the packed columns, there are capillary columns or open tubular columns. They have a much higher efficiency and hence better peak separation than packed columns, but because of their diameters, their capacity is much lower. So typically a packed column can take any volumes from between 1/10 of a microliter to up to 20 microliters. However, capillary columns typically only take up a few microliters or even much less volumes than that. In a capillary column, the walls are coated with the stationary phase or the adsorbent layer, which supports the liquid phase. So the liquid doesn't really look like a liquid. It's a thick viscous liquid typically, and it's coated onto the adsorbent or layer of the stationary phase, as I said. And there can be different kinds of capillary columns, such as the wall coated open tubular, the support coated open tubular, and the porous layer open tubular. And typically the W-COT columns have better resolutions and efficiencies than the support coated open tubular columns. Now the inner diameters of capillary columns are ranging from 0.1 to 0.2 millimeters. The lengths can go up to 105 meters, although there's a wide variety available depending upon the kind of sample you intend to analyze and the range of resolution that you desire. So for example, when you're looking at resolving trans fatty acids, the column length typically recommended is 100 meters. Whereas if you're simply looking to see the fatty acid profile within the serum or a sample, then a 30-meter column can also suffice. The thickness of the stationary phase typically is around 0.25 microns, although it can vary to slightly higher or slightly lower sizes. Stationary phases can typically be either solids or liquids, and solids are often Kieselguhr or synthetic polymers like squalene, and they are much less common as compared to liquid phase. Now, the liquid phase that is coated on, the purpose is to dissolve the components of the samples differentially, be practically non-volatile at the temperature of the column, although this does not always ideally play out, and there is some sample bleed, because of which column conditioning, which will be mentioned later, is necessary. In addition, it is also supposed to be chemically inert and have high thermal stability. However, all these three factors like chemical inertness and high thermal stability are not always present. B, because of certain conditions such as maybe exposure to oxygen at higher temperatures or even at room temperatures, these columns, even when the liquid phase is inert and has high stability, will show some reactivity, leading again, as I said, to column bleed. Typically, this liquid phase is a cured and chemically immobilized liquid polymeric material with the features just mentioned, and examples of these are silicone oils with cyanopropyl groups to change the polarity, and dinonyl phthalate is another one of those groups that is often present along with silicone oils. So here is a representation of the different types of columns, and we are showing you a cross section and the different kind of stationary phases, although you should be aware that there are a much wider range available. I am just listing some of the typical ones, and this is how a cross section of the GC column looks. So there is the polyimide coating, then there's the fused silica column, and the fused silica column is basically a W-cot type of column, which is the wall-coated open tubular column. And as said earlier, W-cot columns are typically more efficient than the support-coated open tubular columns. Now, the typical stationary phases seen in the W-cot or the fused silica columns, which are much more common nowadays, are polysiloxanes, polyethylene glycols, and then the silicon phases along with groups that we just listed in the previous slide. For the plot columns, the typical stationary phases that are seen are styrene, aluminium oxides, and molecular sieves. Now, the capillary columns, such as the fused silica column, which is a modified W-cot, have much thinner walls than glass capillary tubes. These are strengthened by the polyxamide coating that is just shown on the slide, and because of this thinness and their strength, they are flexible and can be wound into coils. They also have a very low reactivity, and because they can be wound into coils, we have seen that the range of the length of columns that can be used is now very high, which is anything, as I said, from 10 meters to up to 105 meters. Now, the other important component of the gas chromatographic system is the detector. What is key to the detector is its sensitivity, which we discussed earlier, the selectivity and the dynamic range, the definitions for which were also discussed earlier. As we said, one of the reasons the gas chromatographic system is so versatile is because of the wide range of detectors that are available with varying sensitivities and application. One would desire from an ideal detector would be a reproducible response to the change in eluent concentration, one of the features of a linear dynamic range, and as far as possible the dynamic range should be also large. Now, the detectors can be either mass sensitive, that is, they are responsive to the mass passing through the detector in a certain time, or they can be concentration sensitive, that is, they are sensitive to the concentration that is passing through the detector in a certain given time. More or less, most of the detectors are mass sensitive. Another desirable feature of a detector should be low noise, that is, it should be able to distinguish very well with the background, and the sensitivity for the background should be low, whereas it should be highly sensitive to the analyte of interest. The response of the detector, which is in the final output we see as a peak, is the voltage output for each unit change in solute concentration. These are the different types of detectors used in gas chromatography, and the chart shows you the type of detector, the type of response, whether the response is mass or concentration sensitive, whether the detector is destructive, that is, can the sample be used after it's passed through the detector or not, and the typical LODs that are characteristic of each of these detectors. So the flame ionization detector, which is the first one listed, is usually the most widely used detector in GC systems, and for this detector to be used, the sample must be combustible. Now the response of the FID detector depends upon the change in the conducting power of ions in an electric field which is produced on burning of the organic compounds in the flame. The flame is typically a hydrogen flame, and this detector is universal to carbon, and its response characteristic is mass. Of course, because the sample is combusted before the readout can be given, it is a destructive type of detector, and its LOD is around 1 picogram per second. The next detector in the list, that is the thermal conductivity detector, detects changes in thermal conductivity. It is also a universal detector, but it is concentration dependent, but it's not destructive, and the LOD is around 500 picograms per ml. Mark the way the LODs are represented differently for mass sensitive and concentration sensitive detectors. The electron capture detector is based on the absorption of beta rays that are emitted by the radioactive source in this detector, which is nickel 63, and this is often used for analyzing pesticide residues in samples. This is also concentration dependent, and its LOD can be as low as 5 femtograms per second. The nitrogen phosphorus detector, as the term implies, responds selectively to most organic compounds that contain nitrogen or phosphorus, and it is also mass dependent. Then we have the flame photometric detector, which is selective, and then next is listed is the mass spectrometric detector, which is mostly universal with a few caveats. It is also mass sensitive, and its LOD can be anywhere from 0.25 to 100 picograms. Now for the analysis of your output, which is the chromatogram, which will typically contain multiple peaks, there are a few principles to be followed, and the basic understanding of the analysis should be that the quantity of each of these components will be directly proportional to its area in the chromatogram. Most of the times the analysis done is qualitative. However, if you have standards against which you are running the sample for analysis and the amount of standard is known, then this can also be a quantitative process. The analysis, of course, starts with looking at just eyeballing the chromatographic peaks that have been obtained. And when packed columns are used, these are typically triangle shaped. In capillary columns, however, when there is good resolution, the signals are straight lines. Now, depending upon the total number of peaks you see, the area of each peak will be represented as a percentage of the total peak area. However, a certain amount of editing is necessary, which I just show in the next piece of the discussion. And the individual mixture components can be identified by comparing using chromatographic standards. Now, standards are those mixtures in which the components have already been identified. The retention time for each of these the components of each of these standards has already been defined, although it may vary somewhat from protocol to protocol. But for the same sample being run under the same condition as the standards, the retention times fairly match those of the standards. These are the general steps in the analysis. So understand that when we load a sample onto a column, the solvent in which the sample has been dissolved will come out first. So before starting to analyze the individual peaks in the chromatogram, we need to edit the chromatogram with the help of the software that has been provided with each of these chromatographic systems. And each of them is, of course, patented by the company which has made the system. So the editing involves removing the solvent peak. Sometimes impurities also give peaks that also need to be removed. And once this has been edited, then each of the peaks is identified by their respective retention time and documented against a standard mixture, which we just said is a mix of pre-identified components. Then the total area of the peaks will be given by each. Of course, nowadays the software is sophisticated. It will give you the area of each peak, but the typical formula that you use for the approximate area, if your peak is well formed and there is no tailing, so this is of course an ideal peak, then the typical formula is given in front of you on the screen. But the chromatographic software nowadays gives you peak areas for the individual peaks, and then the area of each peak will be divided by the total area of all the peaks and multiplied by 100, so you get an idea about the relative amounts of each of these components in the sample that you are analyzing. This is a sample of a gas chromatographic run, and as you can see, it's showing the peaks of a large number of organic compounds, and these range from phenol to aniline to benzyl alcohol, and most of these peaks are very well resolved. They are thin straight lines. A couple of these peaks, the baseline is not completely separated, but it is not of a concern if you are simply doing a qualitative analysis to determine what the components of your sample are. However, for evaluating the actual peak area, some baseline adjustment may be necessary. However, this is close to an ideal chromatogram even in terms of the resolution. Now, of course, we have spoken of how an ideal chromatogram should look like, and you've seen what a good chromatogram looks like, but more often than not, especially during standardization, also while the column is still being conditioned, there may be cases in which there is poor resolution or the tail of the peak is dragged out, called tailing. Also in the lower half, you can see a chromatogram that is ideal, which are thin narrow peaks, and the one next to it is not so good because there is some tailing. Also, the peaks are not very well resolved. Now, the top half of the slide shows some of the reasons or some of the ways in which a chromatogram is not that great. The blue one shows that the baseline is rising as the sample is being analyzed, and this sometimes happens when a conditioning has not been done properly. So when the temperatures rise, then the bleed increases and the baseline can start rising, making it difficult to interpret the chromatogram later on. The other one shows a lot of noise. The one in black shows a lot of noise at the baseline, which is also not a very good chromatogram. A, because of the noise, of course. B, because the smaller peaks will not be able to be resolved. And thirdly, of course, as you can see, there are many peaks that are merging into each other that are also tailing, so the resolution is also quite poor. Now, as we have discussed the different components of the GC system, we also must understand the factors that affect GC separation, and these are related to the GC system components. So first, the carrier gas flow rate is very important in determining the resolution. If the gas flow rate is not optimum, the peaks may not resolve completely and will not touch the baseline. Then again, the temperature or the programming, which is the rate at which the temperature changes across the whole method, will affect the separation of your analytes within a sample. Then again, the column length and diameter, which you know now range from anything between a few meters to up to 105 meters, and the diameter of the column is very critical for the GC separation process. And then the thickness of the stationary phase, which again we know can vary widely, affects GC separation in a major way. Finally, the sample volumes, and we know now that the capacity of a column is much higher when it is a packed column as compared to a capillary column in terms of the sample volume. So when the sample volume is too high, then that means you're typically overloading the column, and so the sample analytes may not resolve to what you desire. So the sample volume based on the expected concentration of the analyte has to be optimized before you start your actual analytical process. This shows the typical layout of a gas chromatographic instrument. The first arrow shows you the sample loading tray in case the system is also equipped with a autosampler. If there is no autosampler, then the loading of the sample onto the column will be done manually. However, in an autosampler, there is a sample loading tray, and then there is the syringe loading compartment, which is the dark glass that you can see in which the syringe is loaded. That syringe will automatically lift samples based on the program that has been set and then load it onto the column. The other important part of the gas chromatographic system that is shown here is the oven in which the column is present, and then the control panel which can allow you to make the settings for the particular program that you want. All of this, of course, will be connected to the user interface for the software that runs the whole and controls and the whole chromatographic process, along with the software that allows you to do the final editing of the readouts that are obtained. Now, before one starts developing a method for a particular group of compounds that one wants to analyze, there are some practical aspects that need to be looked into. First one, of course, is to know whether the analyte that we're interested in looking for or looking at or testing the concentration for is thermally stable or not, whether it is volatile or semi-volatile. So basically, aspects related to the chemistry of the analyte of interest need to be determined before the actual method development process starts. Then, if the analyte is not volatile or suitable for analysis, is it amenable for some chemical modification, such as a derivatization, such as is done as methyl esters for fatty acids, as silylation for hydroxyl and amino compounds? So if the analyte is amenable to derivatization to a compound that can be subsequently analyzed, then it can be used for a method that can be analyzed, or a method that can be applied to the gas chromatographic process. Now, there are mainly three types of derivatization. They are acylation, alkylation, or silylation. Derivatization, apart from changing it or modifying it for its polarity or volatility, can also help it to be tagged with a functional group to improve detection. So, for example, tagging with chlorine is done so that it improves the response of the detector, of the electron capture type of detector. Then the robustness of the column chemicals with regard to its thermal stability need to be determined. And again, there is a wide range of chemicals now available which are part of the column, and the thermal stability of each of these varies. So if the program that is to be run for a particular mixture needs higher temperature for resolution than the thermal stability of the column, then some other column needs to be tested. Then it needs to be determined whether there are elements in the sample that may be corrosive or destroy the column, such as chromic acid or alkali. And before starting out on the method development process and the standardization of the final methodology, the column needs to be conditioned and sometimes activated. Conditioning is a prerequisite before starting any of the programs or methods, and that essentially removes the components of a bleed, essentially puts the column in readiness to accept the sample so that it can be analyzed in an optimal fashion. Before all of this can start, of course, one needs to determine the type of detector that would be best suited for the type of analyte that we are interested in looking at. and the sensitivity of the detector. So typically, if you expect very low levels or your expected levels of compounds such as, say, pesticide residues are not expected to be very high, then you need to choose a detector that shall be capable of detecting your compound in such low levels. So knowing the detector type and sensitivity is very key to the method development process. As we have discussed during the practical aspects of GC method development, derivatization may be needed to convert a compound so that it is amenable to analysis by gas chromatography. One of the examples of derivatization which we do also in our labs is conversion of fatty acids to their respective methyl esters. Now, in this case, it is necessary to convert fatty acids into low molecular weight nonpolar derivatives, which can be analyzed on a column such as a 100-meter column if you need the resolution of the trans fatty acids as well, and on a 30-meter column if you only need to see the fatty acid profile. However, this process of derivatization that is called trans-esterification, when it is converting them into methyl esters, it converts them, as I said, into low molecular weight non-polar derivatives. The good thing about it is that very small amounts of material are required, and in this process the lipids in the sample are first hydrolyzed and then trans-esterification, which is basically an ester exchange process using compounds like boron trifluoride, etc., converts them into the respective methyl esters. So you have the range of fatty acid methyl esters within a sample, which can now be separated on, say, a bis cyanopropyl column. So this is a sample chromatogram from one of the runs in our laboratory. We work primarily on fatty acid analysis with by gas chromatography. So this is a serum fatty acid profile, and as you can see, there is a little bit of a rise in the baseline towards the end of the chromatographic run. So that is not ideal. However, this is the range that you typically observe when you're analyzing serum. This particular sample, actually the serum has been eluted out of a spot of blood from filter paper, and then that has been analyzed, so indicating to you the sensitivity with which this process can detect the different analytes. And for fatty acid analysis as FAMEs or as methyl esters, the detector used is the one that is the most widely used, the flame ionization detector. Now, the applications of gas chromatography, as we said, have a very wide range, and these can be either quantitative or qualitative. And because of the many types of columns and detectors available, because this is a highly sensitive technique, it is used across many industries as well as for research and academia. So environmental analysis is one of the very common applications of gas chromatography. Pesticide residue analysis in water and vegetables for health reasons, vehicle emissions to determine the kind of compounds present in those emissions. In clinical medicine, the application range from testing for blood alcohol to testing for different drugs like nicotine and opioids. In forensic medicine, again, because of its sensitivity, it's used for detecting explosives or trace compounds. Then it's an indispensable tool for consumer goods quality control, because a lot of pharmaceutical quality control and analysis of food is done through gas chromatography. As far as food analysis is concerned, the applications can range from anything from flavor component analysis of edible products to the fatty acid composition of different kinds of, say, vegetable oils that are there in the market, to see what their, say, respective saturated fatty acid content versus the unsaturated fatty acid content is. So these are some of the analysis that is done using gas chromatography. Then again, studying petrol composition, the purity of the solvent in gas refineries is an application in the petrochemical industry. I would like to wrap up with a mention of a specialized type of gas chromatography called fast chromatography, which typically involves using a much shorter length of columns than the wide range available, and they have much smaller internal diameters that allows the analysis time to be much shorter. And these short columns, along with the fast oven temperature ramp rates, so the change in temperatures are much faster. And then the carrier gas goes through with a much higher linear velocity. The column IDs are also narrower and the film thickness is also low. So the combination of these characteristics of the GC system allows it to do the analysis in much a shorter period of time, which is desirable across applications. So students, let us now summarize what we've learned in this module. We've learned that the technique of gas chromatography is highly sensitive and specific, and this is true for analytes that are thermally stable and volatile or amenable to derivatization to compounds with such properties. That is, they can be converted to compounds that are thermally stable but volatile. The flexibility and range that is offered by this technique is due to a number of reasons. One of them is that columns of the wall-coated open tubular type are now available, of which the fused silica is now widely used, and the resolution that is possible with these capillary columns. Further, the analytical process is relatively fast, and there are a number of detectors that can be combined with the columns available that offer a very high level of sensitivity as well as specificities. And of course, we've seen that the detectors can be either mass or concentration sensitive, with varying sensitivities from picograms to femtograms. Now, the other key thing to remember from this is that there are different variables that affect the resolution of the chromatographic process, which is the ultimate goal. That is, to be able to separate compounds that may be similar but can still be separated well enough for them to be analyzed both qualitatively and quantitatively. These variables are the flow rates of the carrier gas, the type of column being used, the thickness of the stationary phase, the length of the column, and the temperature programs that are followed during the analytical process. Thank you.